Hello, everybody. Again, my name is Devin Cairns, and this is part of the carbon process videos in terms of implementing subsurface carbon reactions in BioRT-HBV. And so this is video 2A. It'll come in two parts as I'm going to go over how to set up the shallow zone soil respiration process in BioRT-HBV. So part 2A will go over all of the input files, what we need to include, and then part 2B will be showing you how to set up all these input files and running and looking at the output of the model. So to begin, as you've probably seen in some of the other videos in terms of the input files themselves, we have the following input files, and we will amend the following four input files. So first will be the chemistry or chem.txt input file, and this includes all the model settings, telling the model what species are going to be included in reactions, and then telling the model what reactions we want to simulate. The second input file is the database file, and so this is based on the database file that was used for CrunchFlow, another reactive transport model. The third input file we will change is the initial conditions or CINI.txt input file. So this will have all the initial conditions, your initial species concentrations in your system, and then also the initial conditions and different parameters for your reactions. And then the fourth input file has to deal with the time series of precipitation chemistry. So we have our precip chemistry time series file, and then we also have the numerical experiment precipitation input if you're going to be running any numerical experiments with BioRT-HBV. So to begin, we will first amend the chem.txt file, and I like to amend them in this order just so that I can keep everything straight. And so the three main aspects of amending the chem.txt file we'll need to look at is making sure we have reactions turned on. So we'll look at this transport only line and make sure that it's set to 0 so that we have turned on the reactions. The second portion is we need to make sure we list all of our primary and secondary species of our reactions that we're simulating. And then the third block is we need to look at the mineral kinetics, and this will refer to our reactions that include a solid phase. And then it will also include this label, which will tell the model where to look within the database. So right now we're having, again, because we're going to be simulating the shallow soil respiration reaction, we have the decomposition of organic carbon in the shallow zone, and it's a solid, as you can see here. And so we're telling that this will be a kinetically controlled reaction, in that the model will look in the mineral kinetics part of the database and look for this solid labeled with this test label. So that's how it's telling it where to look in the database. And we will look at the database and compare it to this input file too, so you can see what's going on. But first we need to go over what are primary and secondary species. This will be much more important when we're including more equilibrium controlled reactions and much more important in terms of the weathering reactions. So there should be other videos that explain more in depth about these primary and secondary species. But in terms of setting up this shallow soil respiration reaction, we'll go over it really quickly and show you where to put all of these solutes that come from our reaction. So in terms of our primary species, they're going to be the building blocks of our chemical system of interest. So we need to make sure all of our primary species are those that are produced from these reactions. So our primary species include those that are produced from microbe-mediated bioreduction reactions, mineral dissolution reactions, precipitation reactions, if it's going the other way, and redox reactions. So in terms of our system, we're setting up this shallow soil respiration reaction with the decomposition of organic carbon in this solid organic carbon in the subsurface, as well as the contribution of roots to make dissolved organic carbon and carbon dioxide, dissolved carbon dioxide in the aqueous phase. So in terms of this reaction, we will actually end up, since we're decomposing a solid phase by a microbe-mediated reaction, we're actually going to list all of these as our primary species. So an easy way to think of these primary species are the primary species are those from solid phases and products from the kinetic reactions. And so we have the solid phase and our products of the kinetic reaction, which is DOC and CO2. And again, our secondary species will be more important in chemical weathering and speciation reactions, as these will be species that are made out of our primary species and usually determined via equilibrium controlled reactions. Okay, so now that we've identified our primary species, we can list them within our chem.txt file. And just one note is we always have to make sure that we include pH as a primary species. That's just a requirement of the model. Yeah, so we always have to include pH. You can just put pH this way. You could also put a hydrogen ion as well, H+, but I like pH. So then we list our primary species, DOC, CO2 aqueous, and then our solid phase will all be our primary species. And I like to make sure I follow a kind of an order of best practice, helps me keep everything aligned. And then especially as we're listing these species in other input files, it helps me to make sure if I need to go back and do any troubleshooting, if they're all in the same order, it's easy to track what species which species I may be missing, or maybe what I need to amend. It's much easier to troubleshoot if they're all in the same order. And so again, list your primary species from aqueous species first and then solid phase. So I have pH, then I have my aqueous species, and then my solid phase. Then the second, we'll put our solid phase in the mineral kinetics block. And so I'll specify, again, this solid phase. And again, this is lumped in the model. So we really just tell the model that we want this solid phase that is listed in the database. Okay, and now to really explain the database a bit more, we want to check that what we specified in our chem.txt file matches with what we have in our database, so that we're telling the model to look in the right spot in the database. So first, we'll make sure that we've checked for all of our primary species and that we have our primary species listed as primary in our database. So in our database, we'll have in the primary species block, if you can figure out it's the primary species block, because there'll be a label, usually start of primary or end of primary, which you can see I've shown here. And so we can see that we have, we have two primary species here. And I should have made a cheat sheet here of our database document to see what this is all labeled. So I'll put these two right next to each other really quickly. And so we can see, excuse me, that in terms of our primary species, we first have our species name listed first. Then the second number will be the Dubai-Puckle size parameter here. And then we will put in the charge, but since this is DOC and CO2, it's a neutral charge. So we have 0 for a neutral charge. And then the last number within our primary species block is our molecular weight. So this will be the molecular weight of our primary species. Okay. And so then we check that we make sure what we've listed in our chem.txt file matches our primary species file. It does, so it's all good. So next we'll check our reaction network, and this will be our kinetically controlled reaction. Will be spelled out in this reaction network. And again, this will be in a block that's called mineral. And so you'll see this block in the database by end of minerals here. And then anything above this line will be your reaction networks. So you can see this is the reaction network for our solid phase. And again, we'll pull out the cheat sheet really quickly so we can see what each of these mean, each of these numbers mean. Oh, let me get this the right size. Okay. So we can see in terms of our reaction network, we have our mineral name here first listed. So this is our mineral or our solid phase. Again, it's called mineral phase because this is a database based on crunch flow. However, it doesn't necessarily have to be a mineral in this case, where you consider it just more as a solid phase. So when it says mineral, we consider it more solid phase in a solid phase reaction. So the first will be that solid phase name. Second number is the molar volume. So here's molar volume. The third number is the number of species in the reaction. So there's 2 species that are produced from the decomposition of this solid phase, dissolved organic carbon and carbon dioxide. The next numbers are the stoichiometric coefficients. So this is this A, which we had defined in our equation for DOC, and this is B, which we had defined in our reaction equation for CO2. So the stoichiometric coefficients are here. And then we have the log K array. So this would be the kinetic equilibrium constant for this reaction, and these are all at different temperatures. However, they're all set to the same. So if you want to have different KEQs at different temperatures, you can set that within this array, and you can look up what temperatures correspond to which value if you look in the CrunchFlow database itself. So, and then the very last number is the molecular weight. And so the last thing to check in our database file is our kinetics block. And again, I'll just keep this up so we can look at and compare kind of on our cheat sheet what everything means to what we're looking at in our model. So the first part here is, again, the model will look for the solid phase in this kinetics block. And again, it'll all say end of mineral kinetics so that you can find it in the database, and anything above that will be our mineral kinetic blocks. So in the chemistry file, we've told it to look for this solid phase. So it'll look here. We've told it to look for solid label test. Actually see that this says label default. So the model actually wouldn't read this block because the labels don't match. So we would need to change this label of test to default if we wanted it to read from this kinetics block. And so, and then, yeah, the first label, again, is telling it where to look, and then the type is the type of rate law it follows. So this one follows transition state theory. TST is what that stands for. So this is actually the wrong kinetics block. We would want to go back and look in the database and look for the type of rate law that's a Monod controlled rate law. And so that must be why we have it labeled test, as in the kinetic block labeled test would be a Monod type rate law. And then again, this is the kinetic rate constant, log K. So it's raised to the -10. This activation energy, we're not worrying about it right now. We can also input dependencies. But again, based on our last video where we talked about, we assume that there's no limiting substrate. We don't have any dependence defined in this reaction. Okay, so it seems that we have everything set up in our chem.txt file.